first little introduction is to just tell you what DFT is. DFT is this dynamic field theory. That's the code name we give to the particular form of neurodynamics. And I'll explain a little bit what it is here, but then, of course, the whole course is about that. So I'll just throw out this hypothesis here, and I'll explain it then. So this is this hypothesis that thinking and acting are brought about by the embodied and situated brain that is shaped by evolution and development. It's a very condensed statement that I'll unpack a little bit as we go. And so maybe a way to approach that is to think of what I call cognition in the wild. And I always have this figure of my kids. I'm already a grandfather, so this is very old. These were my kids decades ago when they were playing soccer not on a regular soccer field. And I take this example always to point out two things. You see that, namely, that this activity is actually quite cognitive. There's a lot of cognition in there. So, for instance, if you just look at the visual aspect of that, you have attention, gaze, you can get active gaze shift, where you look around where things are. And actually, to do this efficiently in a game like that, you cannot start a new visual search every time you look for something, right? You will use a scene memory all the time to very efficiently look up stuff. You're already using goals to direct your vision. You're looking at the ball, maybe at the obstacles, at the other players and so on. And that form of memory, the spatial memory, is already going to the core of cognition. Evolutionarily, memory of locations is the oldest form of memory. Very low-level animals have that. And when you run around here, you're building a map like that. Your relationship to the space will change, and you will have a sense for where the goal is and whatever else it is, right? So that's already mentioned. And of course, the game consists of making decisions all the time, right? You make a decision about even where you look and, initiating a step or running or, orienting attention to the ball, or when to kick or when to tackle and stuff like that. And these decisions are influenced by goals, literally maybe goals you want to shoot, or even other goals. Maybe you want to be nasty to your sister or something, right? There's other goals that could play a role. You might actually have to weigh goals against each other. You communicate a lot as you do that. This is actually the most elementary and old form of communication. Supposedly, when we were these hunting animals, we would coordinate our hunting activity. That is one of the oldest ideas. And then, of course, in the village, supposedly families were supporting each other in child rearing because we, as a species, have this extremely long childhood. And that all requires communications. And that is maybe the highest form of cognition. That's very specifically human. And so that is quite continuously embedded in physical activity like that. And there's also coordination in the sense of timing your activity, to kick the ball that's moving, so you can coordinate your movement to hit that. Those who listen to the semester know that that's a real topic in motor control. And then, of course, there is a lot of knowledge and concepts are hidden in there. So, what soccer game consists of. There are even rules of the game and so on. My kids actually didn't really know much about that, but at least they know the ball goes toward the goal. But there's also a much more subtle form of background knowledge that is very difficult for us to currently model and implement in robots. And if any of you has ever looked at robot soccer, I use that in my teaching sometimes, then you know how that sucks just totally. It's much worse than artificial intelligence chess playing, right? So robot soccer is much worse, right? And that reflects that there is a lot of knowledge we have not been able to capture. How slippery is the ground? How hard can you accelerate? How much, how hard to kick the ball when you want to catch up with it again, or how hard to tackle someone if it's your sister or if it's someone else. So that's the famous problem of artificial intelligence, background knowledge, really just meaning hard to formalize, hard to acquire knowledge. And there is a lot of that. And that's what the current AI revolution is trying to make some progress on. And finally, there is constant learning, and actually real learning, not in this artificial intelligence sense of just fitting some parameters. It's learning from experience, right? If you do this, you can't prevent yourself from learning. It will be better next time. And development is, of course, a very important part of that. If you do this stuff like that a lot as a child, then that will be encoded in a sense, or be in your nervous system, and you will behave differently later because you had that early experience and developed the corresponding skills. So all of that is contained in some simple activity like that. And so that's one point, right? That motor behavior is quite cognitive. It's actually oriented to objects, and that involves very much the same sort of things as thinking. Now, the reverse is to say that there are certain properties that are required to achieve that. We call these properties of the underlying neural processes, that they matter also for other activities than just motor control. And so, for instance, when you do these embodied forms of cognition, you have continuous time courses of things. You do continuous stuff in physical world, and you have a continuous state space, right? You physically, you can group in, make a continuum of different speeds or different peak accelerations and force or whatever it is. It's also, space is one of the continuous dimensions, so where you're aiming at, and so there are continuously many movement targets that you could have, but there are also continuously many, levels of force or durations and so on. And these kinds of processes that have these continuous dimensions can be linked to sensory information. That's what you're doing here, of course. Often they're intermittently linked to attention, gaze, and so on, not continuously linked, but can be linked any time. In particular, any processes derived from that can be, as we say, continuously be updated online. That is, you can change your plan online. If the ball suddenly is hit by something else, you can, on the fly with a little delay, correct that. So this is sometimes called grounding in cognition, that everything is sensory motor grounded. This form of acting happens in closed loop. That is, the actions you make change your perception. They change the world and therefore change your perception. And that is an idea that even if you don't do that in the world, if you just internally do stuff, that there are similar things happening. For instance, in mental mapping, that when you do inference in mental mapping, that as a result of an earlier thought, there is now a new context for the next thought. Now, would also be some form of internal closed loop. So in this perspective, the discrete events that are often invoked when people talk about thinking as a form of computation, where you go from one step to the next or make some logical conclusions. Those things are actually, in this perspective, clearly emergent. That is, it does happen that you do make a decision. Now I'm kicking on before I was running, but these emerge from the continuum. It's not like there is some higher level, clocking device that tells you now make a new decision, now make a new decision. No, it's emergent, and that it's also true about categories, and we'll actually look at that in the course a little bit. And finally, this form of learning, this is actually learning, autonomy, we call that autonomous learning, that is learning from behavior that you generate yourself, right? It is not a learning that consists of somebody giving you the result and say, please do that, like what we call supervised learning. It's also not the sort of thing that machine learners call unsupervised learning, because unsupervised learning is also, in a sense, very supervised, because it says, this is an example, this is an example, this is an example of what you learn, right? It's all controlled from the outside when there are opportunities to learn and what the learning is about. While autonomous learning means that you do something and you have to figure out when is a good moment to learn and what to learn about that, what you're doing, right? You have this whole visual array, are you going to learn just anything that you have there, or are you going to actually pick out what is the learning, the aspect that is worth learning? So the embodiment hypothesis, this other side, is that these same properties are relevant for higher cognition, or for cognition that is not sensory motor in an obvious way, for actual thinking, let's say. So this is not the way a lot of other researchers, including especially a lot of philosophers of mind, talk about embodiment. They often, they like to debate the meaning of terms endlessly. And so I use a somewhat different notion here, and I'm quite convinced that that's actually the more interesting notion in the sense of productive for natural science kind of enterprises. In hindsight, it looks very obvious. You know, if you look into the brain, there is no boundary where somehow, you know, everything is sensory motor, and then suddenly you see, this is really a higher cortex or something. No, it's all done in the same style. It all evolved in the same style, and it all emerges also in development in this way. You see that children learn in a sensory motor way, and then gradually more strongly cognitive aspects emerge in their behavior. Right? So that's where. So that's unpacking this hypothesis a little bit. And so the kind of theory we're pursuing here in dynamic field theory is very much inspired by this hypothesis. That's why we're going about it in the particular way we do. And you will learn a lot about that in this course. Now, the other aspect is that it's a neural theory of cognition. And that's where the name neurodynamics comes from, right? And so that means for us that it's what we call a neural process account of thinking and acting. And this word neural process account is actually not so easy to define that in a very formal way. So certainly we mean by that some theoretical accounts that can concretely bring about actions or thoughts, and ultimately robotic demonstrations would be a proof that that's true, but you don't always need that. You can also do mental simulation sometimes. But the emphasis is in doing that, bringing about the processes in a way that respects neural principles. So for instance, not by programming a computer and using concepts like information processing concepts that are not consistent with what we know about the brain. Now, I'll say more about that in a moment. Now, of course, we're not trying to just generate a neural process account for just any kind of acting and thinking, but we're trying to do that to explain laws, right? To explain regularities, principles, you know, that we know from psychology or that we then discover as we do that. And while we all are aware that there is no mathematical model that will predict what you will do in the next moment, right? This is not a naturalistic an account for naturalistic behavior necessarily. It's really about uncovering laws and principles that can be understood. I can deepen that more over the course of these lectures here. So neural theory, so the one thing is, you know, what neural principles, and I just want to make these three contrasts here. So a theory is not just neural just because you say it's somewhere in the brain, right? Even though that is a legitimate question. So cognitive neuroscience, for instance, does a lot of mapping. They have some, for instance, functional terms, actually often kind of computational terms, and then have some paradigms through which they say, well, when you do something that I describe as keeping in memory or I describe as encoding, then certain brain areas are active. So you have made a mapping. For us, that's not yet a neural process account. It doesn't say how that's done. And it is also not needed if you have a neural process account, then to say how it is done in the brain is a separate question. And this is actually not a trivial relationship. There are phenomena that are called, I just forgot that English word. Yeah, I forgot the word, but sometimes you have cases where multiple different neural implementations of a certain functions are available, and you will, depending on context, do it in different ways. For instance, motor system, very famously, there are evolutionary remnants of three systems that have a strongly overlapping function, and you can sometimes do it more cerebellar-like or more spinal or more cortical when you do a movement. This is also not necessarily a theory that is reductionistic. Now, there's another approach that's sometimes called computational neuroscience. And these are not so very sharply defined. Some people would call what we do also computational neuroscience. But let's say there's sometimes an emphasis to say, well, you know, it's ultimately neurons and synapses, and so we have to find out exactly which synaptic mechanism is engaged when, is it, you know, spike time dependent plasticity and things like that. And again, this is something that is a possible level of description. You can sometimes ask, can you change dopamine concentration and change a function that way? That can be interesting, but it's not necessarily the right level of description to understand a particular law or a particular principle. We'll have to find out which principle that is. And the last is just to say, you know, we're actually not considering purely computational approaches, computational in the sense of algorithms that are mathematically described or abstract mathematical principles like optimizing something, or, you know, there's a principle of principle of control and so on, as neural process accounts. So if you build a robot by programming it and using optimal control, that's interesting, but that doesn't provide a neural process account. It's not trivial because people like Carl Friston, for instance, publish papers where they use, for instance, a sophisticated form of Kalman filtering and call that a neural theory of that particular subfield, which is, I think, is cheating. But so we'll be working a lot on this question, what the principles are. And our work is actually really thinking about that and arguing about that. And so roughly, we're having here three steps. One step is just connectionism, ultimately. Connectionism is I would say a tradition, something in well-defined theory, but a certain style of thinking about human performance that uses neural principles at a bit more abstract level than the neurophysics. So it doesn't talk about spiking and membrane potentials, goes a little bit more abstract, talks about activation, the state of neural networks as continuous, discover continuous variables, use sigmoid threshold functions rather than the spike mechanism, and emphasizes that the connectivity leads to the function of a neural network, not necessarily going into the details of synaptic dynamics and so on. And so we're certainly at that level of description. There are more precise ways of characterizing that. We'll look at that in a little while. But there are two ways in which these are not sufficient. And so it's a bit paradoxical because the things we're doing are, technically speaking, just special cases of connection systems. But then I'm saying they have additional principles. And what that actually means, yeah, you have more constraints. It's not just enough to say networks. You have additional constraints. One of them is a form to get these systems to be autonomous. And by that, I mean ways how activation patterns can rise that are not just induced by input or just transduced inputs. And neural networks, as they're currently used in the vast majority of models for human behavior, are conceptually input-output models, even though a lot of them have recurrent loops, but they are just sort of technical things. But they're really just waiting for some input and giving you an answer, ultimately. And all the famous networks are exactly like that. They need a prompt. They don't do anything without a prompt. And the overwhelming majority of human activity is not like that. No? And I raise my arm just because I wanted to do that. I don't need a stimulus to do that, right? And when I'm selecting my next word, I'm not triggered by some other inputs. And there's a neurophysiological evidence that almost all synapses in the brain are part of recurrent loops. You have to do some gymnastics to make that a measurable thing. But if you do that, then you can find out that 95% of the connectivity is part of recurrent connectivity. So our brains are very strongly recurrent, and we call this strong interaction, and we'll make that exact, and that is sort of the additional constraints that we'll be looking at. And then the last step is what we call spatial coupling. That is where there are particular problems in coming to higher cognition, which means ultimately being less dependent on sensory motor stuff, on the link to the sensory motor. And we'll discuss these at some length. And we postulate that there are particular principles of how neural representations that have this autonomous property are coupled. So certain patterns of coupling that lead to that. And that's something I can't explain before we've done that. That will have to do with things like binding, coordinate transforms, some form of argument, binding arguments to functions and things like that. So we'll get to that toward the second part of the course. That's sort of the most advanced part of the course. So in the course we have these keywords we sometimes use. The autonomy, we call that time because it has to do with generating time courses. And the other one we call space, and then the coupling of these space-time integration is how the cognition emerges. And so that's sort of what DFT is about. That's the research program of DFT. And as we pursue that research program, we connect to a lot of different subfields in a lot of psychology, memory and decision making and sequence generation and language grounding and so on. So we'll be touching on a lot of different things. In our research, that means it's very, even at that level, very interdisciplinary, because if you go to a meeting like economics, these are all different sessions, right? And we're in all sessions in a way, which makes it a little bit hard sometimes to understand everything, but it's also then for those who are not interested just in narrow subfields, a lot of people who are from other disciplines, it's maybe also a bit refreshing that you really have an opportunity to look at a lot of different aspects of cognition.